Okay, so let's say I toss this object. I toss a piece of chalk, and the only force that is of any consequence on this guy is the gravitational force. And what is the trajectory of this object? It's parabolic. So the trajectory is a parabola. Okay, so look at this. When you toss an extended object like this, okay, there's only one point on the object that goes on a parabolic trajectory. Okay, that black dot goes on a parabolic trajectory. This and no other point on the bat is going on a parabolic trajectory. This is not a parabola. This is not a parabola. Okay, only that one point goes in a parabolic trajectory, and that one point is the center of mass. Okay, so that's the center of mass of the object. So if you were to squeeze this bat into a single point, that's where you would squeeze it to. Okay, so that's the center of mass. So for instance, your center of mass is behind your belly button, so roughly. Okay, so when you do a somersault or a black backflip or anything like that, that is the point in your body that goes on a parabolic trajectory. Okay, so we'll come to that in a little bit. So when an extended object is tossed in a constant gravitational field, the center of mass travels in a parabolic trajectory. So for instance, if you wanted to find the center of mass of an object like this, what you do is you suspend it from one point, and once it comes to rest, the center of mass is somewhere along that line. And then what you do is suspend it from another point, and the center of mass is somewhere along that line, and that intersection point is the center of mass. So for a flat object, that's how you find the center of mass. But if you wanted to find the center of mass of this coffee cup, for instance, you'd have to suspend it from 3 different points. Okay? And of course, you wouldn't want coffee in the cup. But okay, so that's how you would, in practice, find the center of mass. So if I wanted to find the center of mass of this iPad, okay, I find the point on which it balances. Okay, that would be the center of mass. All right, so for a system of particles, these are all point particles. The center of mass of this system of particles, so this could be a solar system and so on, there is the center of mass. Okay, so the center of mass can be outside the body. It doesn't have to be within the structure of the body. Okay, so here's how you find the center of mass of this guy. See, the x coordinate of the center of mass is each mass times the x coordinate of that mass. So m1 x1 plus m2 x2 plus mx3 is 0. So m1 x1, m2 x2, you take the sum of that and then divide by the total mass of the system. That's how you'd find the x coordinate of the center of mass. Similarly, y coordinate of the center of mass is each mass times the y coordinate of that mass, okay, divided by the total mass. Okay. I brought some demonstrations for the center of mass, but since I'm recording after the lecture, I'll show you the demonstrations. Okay. Here's the z coordinate for the center of mass. Yep.
So the capital M is the total mass?
Capital M is the total mass. So again, I want to emphasize that the center of mass doesn't have to be within the body, it can be outside. And I'll show you a demonstration of that as well. If you have a continuous distribution, okay, these summations get replaced by integrals. Okay, so what you do is, just like in the previous case, you break it up into little pieces. You break the object into little pieces. Okay. there, and then that's the x coordinate of that piece. That's the x coordinate of that piece. That's the mass of that little piece. And then you sum over the entire object, which is doing an integral. Again, capital M is the mass of the entire object. This, of course, will be a volume integral. This mass is the density. dm is the density of the object times the volume of the object. And capital M is also density times the volume. And so the density cancels. And so this is a 3D integral. Okay. So that's how you calculate the x coordinate of the center of mass of a continuous distribution, y coordinate. Okay. And of course, I mean, the center of mass is an important point to find, but for uniform density objects, it's at the geometric center. Okay. So you really don't have to do this integral too often. Okay, so here is a application for center of mass. Okay. Now, this fellow understood the importance of this. Okay. Now, so here's what happens. Okay, so this happened in the 1968 Olympics, I believe. Okay. In a high jump event, here's a bar. I'm showing you a side view. Here's the ground. And so before 1968, here's what would happen. So here's the center of mass of this athlete. Okay, so in a high jump event, most athletes are similarly conditioned. They can really do roughly the same thing. Okay. What they can do is they can take a running jump, and what they can do is lift their center of mass this high. Okay, most athletes, they all can do the same thing. So in the past, so what they would do is they would jump and then cross the bar like this. So they've lifted the center of mass there, and that's the bar they cleared. And most athletes would do this. Mr. Fosbury, what he figured out was he learned a way to jump such that here are his legs, here is his torso, and here is his arms. What happened? What happened to my diagram? All right. So, well, why did he do that? Well, now you see his center of mass is there for that configuration. And his center of mass is really passing under the bar. Well, he's still as good as any other athlete, meaning he can lift his center of mass up to there. So now he can cross this bar because he can lift his center of mass there. Did you guys understand that? So he beat everybody by 6 inches or so. Okay. So that's the Fosbury flop. Okay. So now everybody does that. Okay. So back in the day, that was the high jump technique has evolved, but sort of that's how it started, and that's the worst way of doing a high jump. All right. So we saw that this is Newton's second law, and this was for a particle. But it turns out that this applies to a system of particles as well. So if you have a system of particles like this, There's the momentum of each of those. So the total momentum of the system is just the sum of these momenta. You know how to add vectors, so that's the total momentum of the system. And if there are forces acting on these particles, so let's say F1, F2, F3 are acting on this particle, you add up all the forces, that's the net force. And the net force acting on the system is the rate of change of momentum of the system. Okay? So this law is good for a single particle and for a system of particles. Okay? So, okay, when does this law reduce to F equal to ma? Hmm? When does it? Huh?
Forces are conserved?
No. F equal to d by dt of mv dm by dt times b plus m dv by dt plus ma. So that reduces to that when this is zero, when the mass of the object is not changing with time. Okay? And when you're driving your car, you are burning gasoline, but it's not significantly changing your mass. Okay? When you run, your mass is changing, but it doesn't significantly change, okay, with time. All right, so when the mass of the object is constant, then that reduces to this. All right, so here's the second law for a system whose mass is not changing. Okay, so this is saying the net force acting on the system is equal to the mass of the system, the total mass of the system, times the acceleration of the center of mass. Okay. So, for instance, I don't know if you've noticed this. You guys have all seen firecrackers being burst. Okay, so next time you see a rocket goes up and it explodes, and you will be able to track even in the dark, you can track the trajectory of the main piece. Okay, because let's say if it didn't explode, it would go on a parabolic trajectory, and then it explodes, but the center of mass is still going on this trajectory. And that's where the main piece is also going, and you'll be able to track that. Yeah. Let me show you a little app. So if the net force on a system is zero, and this is the external force is zero, then the acceleration of the center of mass will be zero. The center of mass will go at constant velocity. Okay, so all right, so you'll see that, so I'll make these guys collide and watch for the center of mass. when they're heading towards each other, the external force on them is zero. There's gravity acting on the table, except that the normal force is balancing gravity, and so there's no other force. And friction is there's no friction in there. Okay, so watch the center of mass, and you'll see that the center of mass is going at constant velocity. Okay, so there's this. Oops. There's the center of mass of the object. Okay. Oops. All right, so the center of mass changes direction only when all right. See, the center of mass was, even when they collided, the center of mass was moving at constant velocity. Okay? So that's what this equation is saying. If the net external force is zero, the center of mass acceleration will be zero. Okay. In this case, the center of mass acceleration is g. Okay. All right, now we'll talk about rocket propulsion. So this is a big part of our lives. Okay. So let's say here is a cannon. Okay, initially it's at rest. So its initial momentum is zero. Yep. And there's no external force acting on this. And let's say it fires a cannon. That is an internal force, so the cannon will recoil. Okay, so it has fired a bullet, and the final momentum has to be zero. Okay, the momentum of the recoil of the cannon plus the momentum of the bullet, these two add up to zero. Yep. And that's what a rocket is. So here's a rocket. It expels hot fuel, and so it's total. So imagine this happening in far out in space. Okay. Initially, the rocket starts off at rest. It spews out hot gases, and the rocket will move in that direction. And then it'll spew out more fuel, and it'll go faster. Yeah. And as long as you keep firing your engines, you go faster and faster. The instant you stop firing your engine, you will go at constant velocity. Now here's the neat thing. So here was the rocket in space. Remember, it was initially at rest. What was the initial momentum? Zero. So so now you fired the rocket for 10 minutes. It's got a certain speed. If you track all the hot gases that are going in this direction, the total momentum of all of that will be zero. Okay. So this rocket propulsion depends on the law of conservation of momentum. Okay. All right, now we'll give you a couple of formulas for rocket propulsion. Okay. So imagine this is happening in deep space, away from all gravity. Here's the rocket. Its mass is m plus delta m, and it's flying at velocity v. Okay. And now it shoots out some hot gases whose mass is this, okay? And the exhaust velocity is VE, okay? So that's the speed at which this hot gas come out relative to the rocket. Now, momentum is conserved, so this momentum, which is that mass times this velocity, should equal this momentum. Now, the mass of this guy is m, so m, and he's sped up a little, so there's his momentum. But this hot gas was expelled backwards, And so in the forward direction, initially this hot gas had this velocity, the same velocity as the rocket.
Question.
And then minus the exhaust velocity. So that's the velocity of this hot gas, and there's the mass. Okay, so if this comes out positive, that means relative to the ground, the hot gas is moving forward. Okay? If this comes out negative, then relative to the ground, it's moving to the left. All right, here's the total momentum. So if you cancel out the like terms, what you get is, here's the mass of the rocket times its increase in velocity, that's the exhaust velocity, times the gas you expelled. Now, the gas you expelled, the mass of the gas you expelled, that's how much the mass of the rocket decreased by, so it's negative dm. All right, so we'll rearrange that. So dv equal to minus v dm by m. And now you integrate both sides of the equation. From the initial to final point. Okay. So this is v final minus v initial equal to negative ve log m initial to final. So that becomes v final minus v initial equal to minus ve log m final minus log m initial. Okay, we'll absorb the minus sign, v equal to log m initial minus m final equal to ve times log m initial m final. Okay, so here's an important equation, and what this tells you is, if you want to go at that speed, initial speed of most rockets are 0, you start, okay? If you want to go at that speed, so this should be your initial mass, and there's your final mass. So in a rocket, you're about 90% your fuel, okay? So this is your dry mass plus payload, okay? And this equation tells you how much fuel you should carry, how much fuel you should have. So for instance, the International Space Station, that's going at 8 kilometers a second. Okay, so it starts off from rest. Okay, so that tells you how much fuel you need when you launch the rocket to get to that speed. Okay, so for instance, this kind of stuff, you guys know that Falcon 9 launches from the Space Center, it flies off, and then the first stage is brought back here, lands here. Sometimes the first stage is landing here on a platform in the ocean. Why the difference? Do you want to land here or there? What?
Motion.
You want to land here, you got to spend money to go fish, bring it back here. So why not land here every time? To land here, you don't need as much fuel. All you need is the braking fuel. To land here, you have to fire back and come over here. So if you're launching a heavy payload and you don't have enough room for fuel, then you land here, okay? That's not your ideal place. And if you're launching extremely heavy satellites to geostationary satellites, you might not even have extra fuel to land it back. Then you just lose the rocket. And your customer pays for that. Okay. Do you guys, the first stage of the rocket costs about $60 million. You know how much it costs to fuel the rocket? $250,000. You want to save that baby every time. Okay? It's nothing to refuel and launch a rocket. Okay. All right. So this formula tells you how much fuel you need to get to that speed. Okay. What's the problem here? We haven't accounted for gravity. This is assuming you're launching in space. Of course, we launch everything from Earth, so we'll fix that formula in a second. Okay. Yep.
In the last equation, where's the E represented?
It's exhaust velocity. Okay. And that depends on what fuel you're burning. Okay. So we'll see this, watch this. The hotter the gases come out, the less fuel you need to get to that speed. Okay. But then the hotter the gases come out, the fuel might be toxic and you don't want to deal with that kind of stuff. Okay. It might be explosive and all that. Falcon 9 uses kerosene, which you can get a teenager to pump it up, An irresponsible teenager to pump it up. All right, here's the other equation you'll need. Okay. So this is from this equation. Okay, from this equation. And now take the derivative of that with respect to dv by dt, that's the acceleration. That's the acceleration of the rocket. Again, this is in space. Okay. And that's equal to the exhaust velocity times dm by dt. What is dm by dt?
The change of mass relative to the change in time.
What does that mean? Why is the mass changing?
Because you're expelling.
Because you're burning fuel. This tells you at what rate you're burning fuel. Okay. So the greater the thrust you want a large exhaust velocity, and this tells you what, for a given exhaust velocity, because that depends on what fuel you've chosen. Once you've chosen a fuel, that's fixed. And then this equation tells you at what rate you need to burn fuel to generate that much thrust. Okay. So in this rocket business, if let's say you weigh 100 pounds, okay, so your thrust, you weigh 100 pounds. What can you tell about the thrust? If you want to lift off,
You have to push with 100 pounds.
at least 100 pounds. It has to be greater than 100 pounds. Okay, so most of these rockets, the ratio is 1.7, around 1.7 to 1.8. Okay, so for every 100 pounds, the thrust is about 170 pounds. All right, now let's take gravity into account. What do we want this guy to do? We want it to go from 0 to 8 kilometers a second for him to orbit. That's low Earth orbit. Okay. And with gravity taken into account, so here's the final velocity minus the initial velocity. There's the exhaust velocity log m initial. What is that m initial? That's very good. That's the loaded rocket. So the rocket mass plus the fuel mass. And this is the final mass, the empty shell or whatever. Okay. Hopefully, yeah, you don't want any fuel. There's the acceleration due to gravity, and this is how long you've fired the rocket. Okay. So those are the rocket equations. So let me show you some numbers from the space shuttle program. Okay, so these are the main engines of the space shuttle. Okay. In these engines, it burned fuel from this tank. The fuel it burned, what was the fuel it burned here? These guys burned. Huh? That's Falcon 9. The space shuttle burned liquid hydrogen. They burned hydrogen. Okay, and so the rate at which you're burning You know, jets can't fly too high. Do you guys know why? They can't fly, let's say, more than 100,000 feet.
Not enough air force to things.
You don't have enough oxygen. So this guy is going in space. He's got to carry his own oxygen. So this guy, this tank has. Okay, so there's liquid oxygen, and there's liquid hydrogen. Where is propellant? There, liquid hydrogen. Okay, so that's the fuel. All right, so these main engines were burning liquid hydrogen, and on the launch pad, this sucker is too heavy, so you needed boosters, and these are solid propellant boosters. Okay, so these guys burned for the first 2 minutes, lifted the rocket up, and then it got light enough, and you ejected these. Okay. All right, so the space shuttle, it took about 8 minutes for the space shuttle to get to orbit, to reach an orbital speed of 27,000 kilometers per hour. This corresponds to an acceleration of 15.8 meters per second squared. Okay. The average acceleration. These guys, the solid rocket boosters separated after 120 seconds. The space shuttle's 3 main engines and 2 rocket boosters generated 8 million pounds of thrust. Okay, so 3.55 million kg of thrust. And it weighed 2 million kgs. So this weighed 2 million kgs. And the thrust was 3.55 divided by 2, which is 1.77. So there's the thrust to weight ratio, 1.8. Okay. With this kind of thrust, this is just silly, your 2,000-pound car can have an acceleration of 17.7 kilometers per second squared. If you give this kind of thrust to your car, you will escape in less than a second. Escape Earth's gravity in less than a second. Okay, the main engine exhaust velocity is 10,000 kilometers per hour. 3 times that of a high-powered rifle bullet. At these exhaust speeds, the main engine was burning 12,000 kgs per second. It was burning 6 cars per second, the mass of 6 cars per second. That's the mass of a school bus. That's how much fuel it was burning per second. Each of the shuttle's solid rocket boosters burned 5,000 kilograms per second. 5,000 kilograms is probably a Hummer. For 2 minutes. This is absolutely amazing. So the maximum power output of the space shuttle engine is 37 million horsepower. So for anybody drive a 400 horsepower car here? Okay. What do you drive? Charger?
It's a Duramax diesel.
Okay. So this thing has 100,000 times the horsepower that your car has. Has a power equivalent to 20 Hoover dams. With a Hoover dam, you could run 1 million homes. So with this power, you could run 20 million homes for 8 minutes. Absolutely amazing. And that's just a piddly little thing. Look at the Starship. Okay, so the shuttle's thrust is 32,000 kilonewtons, 32 million newtons. Starship is 72 million newtons. Okay. This is a ship. This is, when they start launching from Florida, you can't miss that. You got to go see it. Yep.
How do they get so much more power in a similarly sized rocket?
Where?
Different fuel, or is it?
Where do you see that?
Like
Oh,
the
this
words-
thing.
Yeah,
Yeah, well, this thing has 33 engines. Burn rate. Yeah. So this is where equations tell you the story. So what your question was, how do you get greater thrust? Well, this, you can only speed up this much, this so much. So the way to increase this number is increase this number. Yeah.